the topic is about hybrid vision transformers for cervical cancer image analysis. So it's basically a review about the vision transformers, basically what we call hybrid vision transformers, and how it is being used, or what sort of research studies were performed for cervical cancer image analysis. So these are pretty much the contents, though it seems like 14 different sections. I would go with, briefly about it so that we can understand where they started and, a little bit history about deep learning and how this got fit into medical image analysis. And then we move on to vision transformers, and then hybrid vision transformers and their key properties, basically what is being said about, like what is being researched on this topic, and my selection of studies, and the architectures and all the other things like limitations and challenges and conclusion. Okay, so introduction to the cervical cancer image analysis. So cervical cancer obviously remains one of the health threat, not a health threat, I would say. Like it's basically a condition where the cancer is seen among women, and most of the cases are detected at the early advanced stages. And of course, it has um, so much of mortality rate within the community. So early detection of the cancer is very much important for its, for the patients to overcome that. So 85% of the cervical cancer cases worldwide are diagnosed only at the advanced stages. So that's very important. That's key here. And traditionally, the diagnostic uh, ways of identifying this is through pap smear test, liquid-based cytology, and colposcopy, but it remains, more labor-intensive and error-prone because it's mostly done manually, in the traditional way of doing things. And since there are a lot of cases coming up, to keep up with the human, uh, you know, uh, in reviewing and coming up with the analysis and making sure that it's accurate, it's kind of complex because of its high observer variability, often resulting in false negatives. So we kind of needed something that can automate this, and pretty much what we call computer aided diagnostics. um, the initial stages actually integrated AI so that it can enhance its accuracy and efficiency in the early cervical cancer detection, overcoming the manual methods. Regarding the evolution, I would say started off with the role of machine learning used in the CAD systems, and then what followed was a drastic improvement to what machine learning was able to do, which is what we call deep learning, and specifically convoluted neural networks that actually was able to bring that substantial improvement in the analysis. So why CNN was even considered? Because um, oops, okay. Uh, it's because the automated learning of the features without manual feature extraction selection, which was actually done for the machine learning algorithms, superior performance in disease classification and lesion detection. It was able to process raw medical images efficiently with, oh, sorry, with all the level of features efficiently, and 3D images were able to be analyzed. And data augmentation, what we call, like, if there is a limited set of data, we can do data augmentation, and which can be effectively used while CNN was used to um, classify these images or segment the images. And finally, training and inference were able to be parallelized using GPUs. So basically, CNN was that threshold point where medical image analysis saw that tremendous improvement in their performance and efficiency. But there are some limitations to CNN, which are limited ability to capture global dependencies. What it means is that when an image is fed into these neural networks, Locally, what we call the color, the texture, the border, those are like um, local features. They were able to um, capture that. The CNNs were able to capture that. But globally, if like based on the complexity of the image itself, that was not possible because these local features were the strong, I would say, advantages of using, capturing those local features were strong for CNNs, but globally it is not. Limited adaptability to varying imaging resolutions, because cancer images taken from various diagnostic instruments, maybe slides, digital images, all these have varying resolutions, which were not, CNNs were not able to have the analysis done with that, with a lot of errors. The analysis was not as good as expected, and reduced generalizability, which led to overfitting, which means like if you train a CNN on certain images, and then when you try to test those images with the or use that model with real-time images, then it is going for either like completely out, like with the not being able to analyze it appropriately, or if it is uh, tested, or the images that were used in real time, and it led to overfitting. If the test image and the actual image that is being tested in production are one and the same, it led to overfitting. So, and it's computationally intensive, and what we consider as a black box problem, because people generally like even today some of these neural networks are still black box. What it means is that we never know how the network actually works, which reduces the explainability part of it. So those are limitations. So vision transformers, it came as a new paradigm, which transformer origins basically talks about, the 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 chat GPTs that we use today, the large language models that we use today, has its neural network being the transformer model, or the transformer architecture, which is quite used frequently in natural language processing challenges, tasks to be completed. And it excels basically in learning long range dependencies, what we just saw, which was a limitation in CNNs. And they were able to capture those relationship within the image, what we call contextual relationship within the data, which means like one part of the image and one extreme part of the image and another extreme part of an image can be contextually linked and mapped so that we understand the image globally. So that was the foundation for the transformers that were applied to the images. And architecture basically, it's really important to understand a brief about how this works. So VIT, what it does is when you send an image, or when you, maybe I'll talk about this in the next slide, which has that architecture. So it basically divides the images into patches, and then flattens the image, and flattens the image, and then the image is converted into vector. Encoding is done, and then it is fed into a classifier, and then you can classify it. Basically that. Basically, VITs have demonstrated impressive results in image classification, segmentation, and detection, but still found limitation in extracting fine-grained local image features, which what we saw as an advantage in CNN. That's sort of a disadvantage in VITs, where they were not able to extract fine-grained local image features that were really important for understanding or classifying the early stage cervical cancer, or detecting this, classifying detection of the cervical cancer. So this is the architecture. I'll briefly tell about it. So initially, it starts off splitting the image into different patches, and then this is quite technical, but I'll just briefly tell that. So splitting the images into patches, and then flattening of these patches, then the patches are then converted into what we call vectors, like the image is converted into numbers, and these are fed into what we call transformer encoder. And then the transformer encoder actually has what we call, the right side, what we call, we have different constructs to it. So multi-head attention norm, MLP. So this construct actually helps in classifying the image, like once it is made into patches, and then once it is flattened and encoded, it is sent into the transformer encoder, and there it gets classified. So basically, this is a little different from how CNN works, convolutional neural network works. Hybridization actually came into existence because VIT also had those issues, were not able to classify the images appropriately because of not able to capture the local features. That's where hybridization basically means combining VITs and CNNs so that you can capture both the local and the global features. So this basically talks about it. And rationale for hybridization is very important because the hybridization actually captures a subtleness that is required, like subtle abnormalities and morphological changes that is required as part of the cervical cancer. And integration, so what we call hybridization is done three ways: parallel, sequential, and hierarchical. And the merging techniques, what we call in a hybridization, has what we call feature reshaping, positional encoding, and fusion module. So these are the techniques that are used for integration. Key properties, combined feature extraction. We can have local and global features extracted. We can use small data sets to achieve that efficiency and performance. Computational efficiencies can be reduced, computational, what you call the cost can be reduced. Uh, Generalization and multimodality can be established, which means like if you train the model on certain set of data, then it can be generalized, wherein you can use the real-time data to get it analyzed appropriately. And training dynamics, where it's like talking about the convergence, where the training and the enabling of faster convergence, where overfitting and real-time utility of the model is established there. Selection of studies, I just briefly want to go through. So it's a non-systematic narrative review. These are the literature review that I did. These are the inclusion criteria, exclusion criteria. These are the keywords that I use to kind of get those literature, studies taken. And time frame of the literature was this. Application and performance. So there were about 12 studies that were taken for this research, and this is a high level understanding of how the models work, like how even hybrid worked or not, stuff like that. So we'll go in detail about it in the next slides, but this is like a very high level understanding of what exactly those studies were, like what the outcome of the studies were. So these are the 12 different hybrid structures, architectures. Um, all involve VIT, which is like the vision transformer and the CNNs. And on top of it, there were some classifiers used, some optimizers used, and also this kind of enabled or fine-tuned the images. I mean, the images generated out of VIT CNNs, and it actually helped in the analysis part. So these are the 12 studies that talked about it. So the first study was about classifying cervical cancer into 7 different types, and pretty much it had a great performance in segmentation and classification, and they used Herlev pap smear data set for the testing and the training purpose there, just to make sure that it achieved that optimal performance. So that used actually what they called adaptive VIT encoder and CNN. That's VIT plus CNN. So the second study had VIT plus support vector machine and particle swarm optimization. So this is a combination of things. So VIT was used to uh, extract the global features, and support vector machine was able to classify it better because support with SVMs, what we call in machine learning algorithm, it's used to classify things, and particle swarm optimization was used to optimize those results. So it achieved an accuracy of 97.78% using CIPAC data, and Harlev data set, it achieved an accuracy of F1 score of 97.805. outperforming the other baseline VITs, CNNs, and other pre-trained models. The Swin transformer combination of CNN also had um, accuracies ranging between 75 to 78% and AUC value, what we call area under the curve value, between 80 to 82%. And then VIT, CNN, and multi-layer perceptron, it also had accuracy of 91.72%, and it did a 11 class classification of the cervical cancer. Um, this one again, the fifth one had the accuracy of 91.02%, a fun score of 94%. Um, this again, the sixth one is VIT plus dense net, which is one variation of a CNN, which achieved that 96% accuracy. Multi-scale window transformer, this achieved an accuracy of 94.7%. VIT plus CNN ensemble, it achieved an accuracy of 95.80. And then the ninth one achieved 98.6. The 10th study had 83.33%. 11th study, which is very quite like very useful to understand that during the training, it just used what we call the weights for training those models. LoRa actually reduced the training time, and it was able to, at the end, it was able to achieve a classification accuracy of 98.9%. And the 12th one had a good accuracy as well. So these are the 12 studies, and I have given the reference of these studies towards the end so that you can take a look at it. I know it's pretty descriptive studies that were made. I just want to tell you that, okay, these are the different hybrids that were taken for the studies, and these are the accuracies that were achieved, and what sort of data set they used, and make sure, and what sort of classification that they did, what was classified actually. So that was important there. Limitations were seen in these studies. So most studies trained and tested their hybrid models on small single institution data sets that lack diversity in patient backgrounds and imaging conditions, which obviously happens for the medical domain, because we have limited data and there isn't data from the diverse background. And the hybrid models analyze only small cropped cell images instead of the entire tissue slides. So this is regarding the images from the slides, and evaluate, like the third point is about the studies evaluated only pre-existing curated data set, not not the real world clinical environments. And reported accuracies on only small or homogeneous data set, which might be because of the overfitting purpose. So if you have the same model done in the real world, it might lead to error or lower performance. So they weren't mentioned about ethical, legal, or regulatory requirements in these studies, which are very crucial for medical AI deployment. Some of the hybrid models are computationally demanding, because even CNNs, what we saw was like computationally demanding, and even some of these hybrids are also computationally demanding. And the combination, what we call like lightweight models, are kind of good in terms of the computational, the cost, but we still don't know how they're going to perform in the real world. So that is one. And finally, most studies are not developed fully. The pipeline of the development was not fully developed. I mean, there are many steps in between, like image pre-processing, segmentation, integration into clinical workflows. All these were not done. This was mostly done in the research setup, but still we can see to it that this showed that sort of performance, so we can consider doing it maybe in the future for some of these hybrids, and see if it actually works in the clinical settings or not. Challenges, so these are the challenges. There is architectural challenge, complexity in communication, training challenges, interpreting, which is like I just talked about, like CNNs being non-interpretable, which is how do the CNN actually works. It's not clear yet. Similarly, we have the same issue with the hybrid models also, but there are some techniques to do it, like explainability, what we call explainability of the model, like how do they even classify that, what features that they take to classify those, for identifying if it's cervical cancer is there, or it's cancerous, non-cancerous, a lot of categories. So ethical regulatory concerns are there, and what we call Finally, computer system validation. So any software that undergoes that is supposedly to be used in clinical settings should undergo what we call computer system validation process. Conclusion, so hybrid VAT and CNN and other hybrid marks a significant advancement, but by effectively bridging the gaps identified as limitation, these have to be improved so that we can improve the detection, classification, segmentation, and there are ongoing innovation in the design, interpretability, and validation of these AI models, which is going to pave way for the robust adoption of these models in the future. And improved performance, computational efficiency, and adaptability will actually improve this overall, so that it is going to advance women's health worldwide by identifying and diagnosing this cervical cancer, like pre-cancer, more efficiently worldwide. So these are the references that I have taken. And one important paper you can see is the 13th reference, which is an image is worth 16 by 16 words. That's exactly the vision transformer research paper that was established in 2020. So you can take a look at it and understand more about this architecture. Thank you.